Evolution of electric motors. The electric motor represents one of the most profound technological achievements in the history of human engineering, serving as the primary transducer of electrical energy into mechanical kinetic energy. From its nascent, highly theoretical origins as a philosophical curiosity in the early 19th century, to its ubiquitous presence as the backbone of modern industrial, commercial, and domestic infrastructure by the late 20th century, the evolution of the electric motor is a testament to iterative engineering, breakthroughs in material science, and massive macroeconomic shifts. The trajectory of motor technology is not merely a chronicle of electrical engineering in a vacuum. It is deeply intertwined with the broader currents of global history, including the Second Industrial Revolution, the fierce corporate battles over the standardization of power grids, the crucible of global warfare, and the eventual reckoning with energy conservation and environmental impact. The pioneers, from electrostatic curiosities to practical rotation. To understand the advent of the electric motor, one must first examine the foundational discoveries regarding electricity and magnetism. Prior to the 19th century, early experimental motors relied entirely on electrostatic forces. The ancient Greek philosopher Thales of Miletus observed around 600 BC that rubbing amber with silk produced an attractive force, a phenomenon that would eventually be recognized as static electricity. In 1600, the English scientist William Gilbert coined the term electricity from electron, the Greek word for amber, and distinguished between electric and magnetic forces. Throughout the 17th and 18th centuries, scientists such as Otto von Guericke, Robert Boyle, Stephen Gray, George von Kleist, and Peter von Musensbruck developed rudimentary machines to produce and store static electrical charges, culminating in Benjamin Franklin's proof in 1752 that static electricity and lightning were identical phenomena. However, electrostatic forces proved inherently impractical for generating sustained, continuous mechanical work, as they could only discharge in sudden, short-lived sparks. The paradigm shifted fundamentally in 1800 following the Italian physicist Alessandro Volta's invention of the electrochemical battery, initially known as the voltaic pile. Volta's creation provided the first reliable source of continuous, persistent electric current, allowing the relationship between electricity and magnetism to be systematically and safely investigated over extended periods. With persistent currents now available, the scientific community made rapid strides. In 1808, Sir Humphrey Davy invented the first effective electric arc lamp. The critical breakthrough for electromotive force occurred in 1820 when the Danish physicist Hans Christian Ørsted made the pivotal observation that an electric current flowing through a wire could deflect a nearby compass needle. This confirmed for the first time a direct and actionable relationship between electrical current and magnetic fields, representing the first recorded instance of mechanical movement induced by an electric current. Later that same year, the French physicist André-Marie Ampère invented the cylindrical coil, known as the solenoid, while François Arago further explored the interactions between copper discs and magnetic needles, laying the mathematical and physical groundwork for electromagnetic force generation. The conceptual leap from simple electromagnetic deflection to continuous physical rotation was achieved by the British scientist Michael Faraday. On September 3, 1821, working in the basement of the Royal Institution in London, Faraday demonstrated the principle of electromagnetic rotation. By suspending a stiff wire in a pool of mercury that contained a permanent magnet, Faraday showed that the wire would continuously orbit the magnet as long as an electric current flowed through the circuit. While Faraday's device was a major scientific breakthrough and the theoretical ancestor of all electric motors, it lacked the mechanical configuration to produce useful work and was regarded largely as a philosophical instrument. Throughout the 1820s, other scientists expanded on these principles. In 1822, the British physicist Peter Barlow invented Barlow's wheel, the first device powered entirely by electromagnetism. Between 1827 and 1828, Ányos Jedlik, a Hungarian physicist, began experimenting with electromagnetic coils and subsequently developed the first commutated rotary electromechanical machine, demonstrating a device that contained a stator, a rotor, and a commutator. The translation of theoretical electromagnetic rotation into practical work-producing machinery required a mechanism to continuously reverse the direction of the current within the rotating coils. Without this reversal, the rotor would simply align with the magnetic field and stop. A device known as a commutator was required to ensure that the magnetic forces perpetually pushed the rotor in a single continuous direction. The English scientist William Sturgeon solved this engineering challenge in 1832 with the invention of the first commutator-based direct current electric motor that was actually capable of turning external machinery. Building upon Sturgeon's foundational work, the American blacksmith and inventor Thomas Davenport, working alongside his wife Emily Davenport, developed a significantly more robust direct current motor. In 1834, Davenport secured the first patent for an electric motor that possessed sufficient power to perform practical, albeit small-scale, tasks. Davenport successfully used his invention to operate a small printing press and to propel a model trolley around a circular track, hinting at the vast future potential of electric traction. Despite these impressive mechanical triumphs, early direct current motors were severely hampered by their power source. Zinc-based chemical batteries were prohibitively expensive, massive, and highly inefficient, rendering early electric motors commercially unviable when competing against the ubiquitous and fuel-efficient steam engine. Interestingly, early pioneers like Hippolyte Pixii discovered that by running these early motors backward via external mechanical force, they could function as generators, a realization that would eventually solve the power supply problem. The mid-19th century witnessed crucial structural advancements that defined the internal architecture of almost all subsequent rotating electrical machines. In 1856, the German engineer Werner von Siemens introduced the double T armature winding, representing a massive leap forward in motor design. Siemens was the first engineer to place the copper wire windings into physical slots cut directly into the iron rotor. This specific design radically reduced the air gap between the rotating armature and the stationary magnets of the stator, which vastly improved the magnetic flux linkage and the overall efficiency of the machine. The slotted armature design was so demonstrably superior that all previous surface-wound designs rapidly vanished from the commercial market, establishing a structural paradigm that remains the absolute standard in modern motor manufacturing to this day. Siemens initially produced around 50 of these devices for the Bavarian railways to deliver pulses for telegraph systems, though they had to be operated by hand as they did not yet supply continuous electrical energy. During the 1860s, the theoretical understanding of these machines was perfected when the British physicist James Clerk Maxwell summarized all current knowledge of electromagnetism into 20 fundamental equations, which were later reduced to 4 elegant equations using vector calculus by Oliver Hayside. On the practical side, the Siemens double T armature still possessed a significant flaw. It produced a highly pulsating direct current. To resolve this, the Belgian engineer Zenobe Théophile Gramme invented the anchor ring, commonly known as the Gramme ring, in 1871. This invention produced a smooth, continuous direct current voltage and allowed the motor to operate with vastly reduced torque ripple, placing Gramme's machines in fierce competition with Siemens designs. Gramme's design was subsequently optimized between 1872 and 1875 by Friedrich von Hefner-Alteneck, a close associate of Werner Siemens, who developed the drum armature. By wrapping the copper wire around a solid cylinder-shaped core and utilizing bundled iron wires instead of a solid block of iron to reduce parasitic eddy currents, Hefner-Alteneck established the foundational geometry and material strategy for the modern direct current motor. The War of the Currents and Motor Standardization. By the 1880s, the development of the electric motor became inextricably linked to the fierce commercial battle over electrical power distribution, an era universally known as the War of the Currents. American inventor and businessman Thomas Edison had established the first investor-owned electric utility in 1882, basing its entire infrastructure on low-voltage direct current. Concurrently, direct current motor technology reached a new milestone of practical utility thanks to the brilliant engineering of Frank J. Sprague, a former employee of Edison. In 1884, Sprague left Edison's firm to establish the Sprague Electric Railway and Motor Company. By 1886, Sprague introduced a revolutionary constant-speed, non-sparking direct current motor equipped with fixed brushes and regenerative braking capabilities. Sprague's motor was the very first to maintain a constant speed under varying mechanical loads, an attribute that made it ideal for the burgeoning industrial sector, electric street railway systems, and electric elevators. Sprague's motor was so effective that Edison publicly endorsed it as the only practical electric motor available on the market. Sprague utilized his innovations to build the first successful large-scale electric street railway in Richmond, Virginia in 1888. His regenerative braking system, which returned power to the main supply system when the vehicle decelerated, proved essential for both traction and vertical transport. By 1889, Sprague's highly reliable equipment was being integrated into 110 electric railways across several continents. Edison eventually bought out Sprague's company in 1890, leading Sprague to pivot toward electric elevators, where he developed the Sprague-Pratt electric elevator, a system that ran faster and handled larger loads than traditional steam or hydraulic elevators. Sprague would later devise the Wilgus-Sprague bottom contact third rail system for railroads and invent multiple unit train control systems, fundamentally shaping urban public transportation. Despite the immense success of Sprague's direct current motors, Edison's direct current distribution system faced a severe physical limitation that threatened its long-term viability. Direct current could not be easily or efficiently converted to higher or lower voltages. Transmitting low-voltage direct current over long distances resulted in massive energy losses due to the electrical resistance of the wires, necessitating incredibly thick copper cables and requiring power generation stations to be located within a mile of the end user. Conversely, alternating current, which reverses directions dozens of times per second, could easily be stepped up to very high voltages via transformers for highly efficient long-distance transmission, and then safely stepped down for indoor use. Recognizing this vastly superior transmission efficiency, the American entrepreneur and engineer George Westinghouse introduced a rival alternating current-based power distribution network in 1886. Edison, fiercely defending his direct current patents and the massive capital investments in his existing infrastructure, launched a vicious propaganda campaign to brand alternating current as highly dangerous. Edison and his associates, most notably an electrical engineer named Harold P. Brown, orchestrated highly publicized events where they deliberately electrocuted stray animals, including dogs and old horses, using alternating current to convince the public that Westinghouse's system was a lethal menace. This smear campaign even extended to the covert funding of the first electric chair used for capital punishment in New York, deliberately using an alternating current generator to permanently associate the technology with death. While Westinghouse possessed a demonstrably superior transmission system, alternating current critically lacked a practical, reliable motor for industrial applications. This massive technological void was definitively filled by the brilliant Croatian-American inventor Nikola Tesla. Between November and December of 1887, Tesla filed 7 revolutionary patents detailing a complete system of polyphase alternating current power transmission, generators, transformers, and the crowning achievement, the polyphase induction motor. Tesla's induction motor was a masterpiece of conceptual engineering. Rather than feeding electric current directly to the spinning rotor via physical brushes and a commutator, components that were prone to rapid wear, severe sparking, and catastrophic failure in direct current motors, Tesla's design relied on a rotating magnetic field generated entirely by the stationary stator. This alternating magnetic field wirelessly induced an electric current in the conductive bars of the rotor. The induced current in the rotor, in turn, created its own magnetic field, causing the rotor to spin in perpetual pursuit of the stator's rotating field. The complete elimination of physical commutators and sliding electrical contacts made the alternating current induction motor incredibly rugged, remarkably simple, highly efficient, and virtually maintenance-free. Westinghouse quickly recognized that Tesla's motor was the essential missing link needed to assure the total victory of his alternating current grid. He visited Tesla's laboratory and purchased the patents for $60,000, which included cash, stock in the Westinghouse Corporation, and generous royalties based on the horsepower of electrical capacity sold. Contemporaneously, in Europe, similar theoretical and practical breakthroughs were occurring in parallel. The Italian physicist Galileo Ferraris had independently developed the theoretical foundation for the rotating magnetic field in 1885, though he incorrectly believed such motors could never exceed 50% efficiency. In 1887, the German engineer Friedrich August Haselwander developed the first three-phase synchronous motor, although he faced regulatory resistance from the German Postal Authority, which feared the machine would interfere with telegraph lines. Finally, in 1889, the Russian-born engineer Mikhail Dolivo-Dobrovolsky, working for the German company AEG, built the highly successful three-phase cage induction motor, cementing the European commitment to alternating current. The overwhelming superiority of the alternating current system was definitively proven when Westinghouse and Tesla successfully illuminated the 1893 Chicago World's Columbian Exposition using alternating current power, and subsequently harnessed the massive power of Niagara Falls for long-distance alternating current transmission. The alternating current induction motor emerged victorious from the War of the Currents, dictating the permanent standardization of the global power grid. To this day, the three-phase squirrel cage induction motor remains the most frequently produced industrial machine for power ranges of 1 kilowatt and above, serving as an enduring testament to Tesla's elegant solution for converting electrical energy into mechanical motion. The industrial boom and the second industrial revolution. The widespread availability of reliable alternating current power grids and the rugged durability of the induction motor catalyzed a profound paradigm-shifting transformation in industrial manufacturing during the Second Industrial Revolution, an era of rapid industrialization generally dated from 1870 to the onset of World War I, but whose effects reverberated deeply through the 1920s and 1930s. Prior to large-scale electrification, factories were entirely dependent on massive, centralized prime movers, typically enormous reciprocating steam engines or massive water turbines. Mechanical power was distributed throughout the entire factory utilizing a system known as the group drive. This highly inefficient system consisted of extremely heavy, ceiling-mounted line shafts and miles of dangerous, fast-moving leather belting that physically connected the central power source to every individual mechanical tool on the factory floor. This strictly mechanical paradigm severely limited industrial efficiency and architecture. Factories had to be constructed as heavy, dark, multi-story structures with heavily reinforced floors specifically designed to support the tremendous vibrations of the steam engines and the immense dead weight of the overhead steel shafting. Furthermore, the group drive system was deeply inflexible. If the central steam engine failed, the entire factory ceased operations immediately. Conversely, if only a single machine needed to be run during a shift, the entire massive shafting system had to be kept in continuous motion. resulting in tremendous frictional energy losses. In the early days of electrification, factory owners simply replaced the central steam engine with a single, massive primary electric motor to turn the existing shafts, missing the true transformative potential of the technology. The true revolution occurred when the introduction of smaller, highly reliable electric motors sparked the transition from the group drive to the unit drive or individual motor drive system. By the 1920s, affordable, small-capacity electric induction motors began to be mass-produced, allowing engineers to directly attach a dedicated motor to every individual machine and tool. The macroeconomic impact on industrial productivity was monumental. The unit drive system completely eliminated the need for overhead line shafts, which allowed industrial engineers to radically rethink factory layouts from the ground up. Machinery could now be arranged sequentially to optimize the logical flow of materials and assembly, rather than being clustered awkwardly around a central power shaft. This newfound architectural freedom allowed for the construction of lighter, single-story, sprawling linear factories, significantly reducing capital construction costs while drastically improving workplace illumination and safety. Energy losses plummeted because individual machines could be turned off independently when not in active use. The scale of this transition was breathtaking in its rapidity. The share of manufacturing horsepower generated by individual electric motors surged from 23% in 1909 to 77% by 1929. By 1929, about 70% of all manufacturing activity relied on electricity, serving as a textbook illustration of capital-saving technological change that enabled the high-speed assembly lines pioneered by figures like Henry Ford. While massive induction motors revolutionized the heavy factory floor, a different class of machine, the fractional horsepower motor, revolutionized commerce and fundamentally altered the domestic sphere. A fractional horsepower motor is defined as an electric motor with a rated output power of less than 1 horsepower, making them small enough to be integrated into portable consumer goods. The aggressive push for urban electrification in the early 1900s created a vast new market for electromechanical consumer products. In 1905, Chester Beach, an employee of the Hamilton Beach Company, invented a reliable, high-speed fractional motor. The company swiftly integrated this motor into a commercial milkshake machine, the Cyclone drink mixer, introducing it in 1910. It was sold extensively to urban drugstores for use in soda fountains, effectively launching the modern electromechanical appliance industry. By the 1920s, as household electrification rapidly expanded beyond wealthy urban centers, fractional horsepower motors found their way into washing machines, vacuum cleaners, and early electric refrigerators. The social implications of this technological diffusion were deeply complex. Before the 1920s, household labor in a world without electricity or running water was exceptionally arduous, requiring immense physical exertion. The integration of electric motors into the domestic sphere was initially heralded in advertising campaigns and home economics magazines as a liberating force that would free women from the crippling drudgery of household chores, transforming the home into a highly efficient, small factory. However, deep historical and sociological analysis reveals a much more nuanced reality. The advent of the electric washing machine, the electric iron, and the motorized vacuum cleaner did not necessarily result in more leisure time. Instead, they drastically elevated societal standards for personal and domestic cleanliness. Because motorized appliances made it physically easier to wash clothes and clean rugs, society began to expect these tasks to be performed much more frequently. Consequently, the net effect of a decline in hired domestic servants, combined with the mechanization of household chores, actually left middle-class and upper-class women performing more localized, continuous household labor in the middle of the 20th century than they had been doing at its start. Economically, however, the fractional motor was an undisputed triumph. It drove a massive new wave of industrialization, moving manufacturing from purely mechanical devices towards a vast array of electromechanical consumer goods, creating entire new manufacturing sectors and laying the permanent foundation for the modern household appliance industry. Mass production, standardization, and the crucible of war, 1920s to 1960s. As electric motors became ubiquitous across every facet of the global economy in the 1920s, the sheer variety of proprietary designs created significant logistical nightmares for industrial end users. Replacing a failed motor required purchasing an exact replica from the original manufacturer, as mounting hole placements, shaft heights, and overall frame dimensions varied wildly from brand to brand. Recognizing that this lack of interchangeability was stifling industrial growth, the National Electrical Manufacturers Association, NEMA, was founded in 1926. NEMA established standardized frame sizes, mounting dimensions, and performance criteria, ensuring complete physical interchangeability across different manufacturers. NEMA's standardization efforts progressed through three distinct generational eras over the following decades. The pre-1952 original frames established the first baseline for interchangeability. However, continuous advancements in internal materials, superior synthetic insulation, and better cooling techniques allowed engineers to pack significantly more horsepower into much smaller physical dimensions. To reflect these advancements, NEMA introduced the more compact U-frame standard in 1952. By 1964, further breakthroughs in high-temperature insulation prompted another major industry-wide re-rate, resulting in the introduction of the T-frame, which remains the predominant standard for industrial motors in North America to the present day. Under the NEMA classification system, the dimensions of a T-frame motor follow precise, standardized geometric rules. For example, in a NEMA 145T or 324T frame, the first two digits of the frame number dictate the shaft height, the distance from the center of the shaft to the mounting surface. Dividing the first two digits by 4 yields the exact shaft height in inches, meaning a 145T frame has a shaft height of exactly 3.5 inches. The third digit indicates the distance between the center lines of the mounting bolt holes from front to back, while suffix letters provide crucial information regarding mounting configurations. For instance, a C or D suffix indicates a specific type of flange mount designed for direct attachment to equipment. Internationally, the International Electrotechnical Commission, IEC, adopted a similar, highly rigorous standardization system utilizing metric measurements, ensuring global supply chain consistency and engineering reliability. Meeting the exponentially surging global demand for electric motors required abandoning slow, labor-intensive manual production methods. In the early days of motor manufacturing, highly skilled laborers painstakingly wound copper wire by hand over mandrels and carefully pushed the delicate coils into the narrow stator slots. This process was incredibly tedious, time-consuming, and highly prone to human error, often resulting in inconsistent wire tension, damaged insulation, and catastrophic electrical shorts. In the 1940s and 1950s, the industry began a massive transition towards semi-automatic and eventually fully automated winding machinery. Prior to this, manual winding limited industrial productivity, but the introduction of mechanization allowed factories to overcome these bottlenecks. Pioneering companies like Globe Tool and Engineering, driven by innovators and executives such as Harry W. Moore, who secured crucial motor winding patents, developed advanced machinery that utilized mechanical arms and automated spools to handle the copper wire. This significantly accelerated the winding process while maintaining uniform tension. Other mid-century firms also entered this highly specialized market to meet post-war demand. For instance, the Passus Machine Corporation, founded by Chris Passus in 1952, specialized in contract engineering and supplied advanced automated motor winders to the broader manufacturing industry. further refining the mass production of electromechanical components. The integration of computer numerical control technology in the latter half of the 20th century represented the ultimate evolution in winding automation. CNC machines allowed manufacturers to precisely program the rotation, traverse, and tension of the copper wire, delivering unparalleled speed, exacting precision, and absolute consistency across millions of units. Furthermore, assembly techniques for the iron stator core itself evolved dramatically. Rather than merely stacking steel laminations manually, manufacturers developed sophisticated automated welding and cleating techniques. Cleating, which involves V-rolling and flattening a strip of soft steel down a dovetail slot on the exterior of the stator stack, offered a cost-effective way to secure the core with minimal impact on its electrical properties, greatly reducing labor costs and improving the mechanical rigidity of the finished motor. The outbreak of World War II functioned as a brutal, high-stakes catalyst for technological acceleration across all engineering disciplines, and electric motors were no exception. The military demanded motors that could survive extreme temperature fluctuations, high altitudes, caustic environments, and violent mechanical vibrations. The war period aggressively accelerated the development of highly precise motor control systems and elevated reliability standards far beyond civilian requirements. In the realm of aviation, the increasing complexity of combat aircraft necessitated a fundamental shift in electrical power generation. Early interwar aircraft utilized rudimentary low-voltage direct current systems, typically 6V or 12V, derived from automotive technology. By 1936, these were upgraded to 28-volt direct current systems to handle the growing arrays of onboard radios, heated flight suits, and exterior lighting. However, the post-WW2 era mandated a total transition to alternating current AC generation systems for heavy bombers and jet aircraft. Alternating current generators were significantly smaller, lighter, and offered vastly higher power densities, which were critical for the emerging more electric aircraft paradigm, wherein electrical actuators and high-torque motors began replacing heavy, vulnerable hydraulic systems for moving control surfaces and landing gear. Simultaneously, the war necessitated the rapid, widespread advancement of electric servo mechanisms. Closed-loop servo motors, which utilize sophisticated position feedback encoders to achieve exact angular or linear adjustments, were deployed extensively for the first time in military applications. These highly responsive motors were integrated into radar tracking systems, anti-aircraft searchlights, and naval gun fire control systems on battleships, requiring tracking speeds and targeting accuracies that were physically impossible to achieve with manual hand cranks. In naval warfare, submarine technology relied heavily on advanced electric motor applications. Submarines such as the American Gato class heavily utilized early hybrid electric propulsion systems. Operating on the surface, 4 massive diesel engines propelled the vessel while simultaneously generating electricity to charge massive banks of lead-acid batteries. When submerged, the diesel engines, which required atmospheric oxygen, had to be shut down. The submarine was then propelled entirely by 2 massive high-torque electric motors drawing power from the batteries, allowing for stealthy underwater operation for up to 48 hours at speeds up to 9 knots. Furthermore, companies like Ward Leonard, which had previously pioneered electric motor control systems for early submarines and warships, converted all their facilities entirely to war production, supplying advanced lightweight resistors and control rheostats that allowed commanding officers to accurately maneuver massive transatlantic vessels and high-intensity searchlights. Materials, cooling, and thermal management, 1950s to 1980s. The post-war decades leading up to the 1980s were characterized not by radical new theories of electromagnetism, but by a relentless, highly technical, and incremental optimization of materials science, thermal management, and magnetic efficiency. The core of any alternating current electric motor is constructed from laminated steel, which serves to conduct the magnetic flux generated by the stator windings. However, exposing solid steel to rapidly alternating magnetic fields induces parasitic eddy currents circulating within the metal. These eddy currents generate immense amounts of waste heat and actively sap the motor's mechanical power, severely reducing efficiency. To combat this phenomenon, motor cores are never made of solid iron. Instead, they are constructed from hundreds of very thin steel sheets, or laminations, each electrically insulated from one another by a microscopic coating to block the flow of these parasitic currents. Between 1950 and 1980, the metallurgy and production of these laminations underwent profound improvements. Following the first production of cold-rolled, non-oriented electrical steel strip around 1954, the industry rapidly developed various grades of steel with strict gauge accuracy, good weldability, and enhanced punchability. Manufacturers universally shifted to utilizing high-quality silicon steel, which is an iron-silicon alloy containing between 0.5% and 3.5% silicon. The deliberate addition of silicon fundamentally altered the material's physical properties, simultaneously decreasing its coercivity while drastically increasing its electrical resistivity, thereby aggressively strangling the formation of eddy currents. The steel industry developed two primary types of electrical steel for the energy sector: grain-oriented electrical steel, GOES, and non-oriented electrical steel, NOES. GOES is manufactured with a strong crystallographic texture, aligning the grains in the direction of rolling to provide vastly superior magnetic properties in a single direction, making it ideal for stationary applications like power distribution transformers. Conversely, NOES is engineered to possess highly isotropic magnetic properties, meaning it performs equally well in all directions, which is an absolute requirement for the rotating multi-directional magnetic fields inside electric motors and generators. Mass production techniques, such as continuous slab casting implemented in the 1970s, allowed manufacturers to produce high-quality cold-rolled NOES in increasingly thinner gauges, often between 0.2 mm and 0.65 mm, drastically cutting core losses, reducing motor weight, and significantly boosting overall motor efficiency. Heat is the ultimate enemy of the electric motor. The operational lifespan of a motor is strictly dictated by the thermal endurance of its internal winding insulation, which separates the copper wires from each other and from the grounded steel core. Historically, early 20th century motors utilized Class A insulation systems, employing entirely natural materials such as cotton, silk, and paper coated in organic shellac or varnishes, or immersed in a dielectric liquid. These organic materials degraded, became brittle, and carbonized rapidly under high temperatures. As industrial motor designs became more compact to save weight and materials, their internal heat densities rose significantly, necessitating vastly superior thermal protection. In the late 1930s and 1940s, the chemical industry introduced revolutionary synthetic polymers, and the popularization of silicone resin paved the way for higher temperature ratings in electrical enclosures. By the 1950s and 1960s, manufacturers transitioned to high-temperature Class F systems, rated for continuous operation at 155 degrees Celsius, and Class H systems, rated up to 180 degrees Celsius, which quickly became the modern industry standards under organizations like the National Electrical Manufacturers Association, NEMA. Materials like woven fiberglass, epoxy resins, Mylar, a highly durable polyester film, and Nomex, a highly heat-resistant aramid paper, became standard components in motor slots and phase insulation. Manufacturers developed sophisticated composite materials such as NMN, which consists of a layer of Mylar or polyamide film sandwiched between two layers of Nomex paper. These triple-ply laminates provided extraordinary dielectric strength, exceptional flame retardance, and immense mechanical toughness. Similarly, DMD insulation materials utilized high-temperature non-woven polyester to achieve Class F ratings. The critical importance of these precise temperature ratings is governed by the Arrhenius equation, frequently adapted in the motor manufacturing industry as the rule of 10. This principle dictates that if a generator or electric motor's total operating temperature is reduced by exactly 10 degrees Celsius, the thermal life expectancy of the insulation system is approximately doubled. Conversely, for every 10 degrees Celsius the internal operating temperature rises above the insulation's maximum rated temperature, the thermal life expectancy of the motor is reduced by 1/2. These advanced synthetic insulators allowed modern motors to survive severe thermal and mechanical stresses that would have quickly incinerated earlier natural fiber designs, vastly increasing industrial reliability across global supply chains. As electric motors moved out of clean, controlled environments and into increasingly hostile industrial, agricultural, and outdoor settings, the methods used to manage internal heat evolved into two highly distinct enclosure designs, primarily the open drip-proof ODP motor enclosure and the totally enclosed fan-cooled TEFC configurations. The ODP motor enclosure features open vents stamped into the casing that actively draw ambient outside air directly into the motor to flow over the hot internal copper windings and iron core. Because the cooling air is in direct physical contact with the primary heat sources, ODP motors dissipate heat exceptionally efficiently. This superior thermal management often results in higher operational efficiencies, a higher service factor, and lower overall manufacturing costs due to the use of less material. However, this open-air design renders the sensitive internal components highly vulnerable to airborne dust, moisture, and chemical contaminants, strictly limiting the deployment of ODP motors to clean, dry, indoor environments. To address the severe demands of harsh industrial, outdoor, and particulate-heavy environments, the TEFC motor was developed and perfected. In a TEFC design, the motor is completely sealed off, preventing outside air from freely circulating through the interior. Cooling is achieved via a small external fan mounted on the rear of the motor shaft, protected by a metal shroud. This fan forcefully blows ambient air over highly conductive ribbed cooling fins cast directly into the exterior of the motor frame. While TEFC motors provide vastly superior protection against environmental ingress, preventing dust from insulating the windings or destroying the bearings, typically achieving IP44 or IP54 ratings, they represent a necessary engineering compromise. Due to their complex construction and reliance on indirect heat transfer, TEFC motors are significantly heavier, generally more expensive to manufacture, and slightly less energy efficient at heat dissipation than their ODP counterparts. Magnets, power electronics, and the energy crisis, 1960s to 1980s. A critical milestone in the evolution of precise motor technology was the invention of the brushless direct current motor, BLDC, in 1962. Traditional brushed direct current motors suffered inherently from the physical friction of solid carbon brushes sliding continuously against rotating copper commutators. This physical contact generated significant heat, caused rapid mechanical erosion, created electrical noise, and severely limited their use in high-power applications, aerospace, and modern HVAC systems. Brushless motors brilliantly inverted this design, placing the permanent magnets on the spinning rotor and using sophisticated electronic switching to sequence the stationary stator coils, entirely eliminating mechanical wear points. However, despite being invented in 1962, the widespread commercial adoption of brushless motors was delayed for nearly 2 decades due to the severe limitations of existing magnetic materials. Traditional ferrite, ceramic, and alnico magnets could not generate a sufficiently strong magnetic flux in a compact space to make the design competitive. The massive breakthrough arrived through the relentless development of rare earth magnets. In the mid-1960s, Dr. Carl J. Stratt and his colleague G. Hoffer, working at the United States Air Force Materials Laboratory alongside Alden Ray at the University of Dayton, discovered that alloys of yttrium and cobalt possessed by far the largest magnetic anisotropy constant of any material then known. This research culminated in the development of samarium cobalt (SMCO) magnets, specifically formulations like SMCO5, which generated significantly stronger magnetic fields, higher temperature ratings, and higher coercivity than any previous permanent magnet. These SMCO magnets finally enabled the mass production of highly compact, incredibly powerful servo and brushless motors, which were immediately adopted for military radar sets and precision aerospace applications. However, the technology soon faced a severe macroeconomic hurdle. In the late 1970s, a major geopolitical crisis and violent political unrest in Zaire, now the Democratic Republic of Congo, caused the global price of raw cobalt to spike dramatically. This massive supply shock heavily incentivized international researchers to find an alternative rare earth formulation that did not rely on volatile cobalt supplies. By the early 1980s, this intensive research resulted in the invention of neodymium iron-boron magnets. Neodymium magnets offered even higher magnetic flux densities at a significantly lower raw material cost, unleashing the modern era of ultra-efficient, high-torque miniature motors. The late 1980s also saw further innovation when scientists Jerry Jenko and Norman Smith patented a revolutionary brushless motor utilizing a stator embedded directly into a printed circuit board, eliminating traditional wire winding and heavy iron laminations entirely to reduce weight and manufacturing costs. As the computer and electronics industry exploded in the 1970s and 1980s, an older motor concept found renewed, vital importance: the stepper motor. Originally conceptualized in the late 19th century for automated telephone exchanges, the stepper motor differs from traditional continuous rotation motors by converting digital electrical pulse signals into precise, corresponding angular or linear displacements. Because the angular displacement is strictly proportional to the number of input pulses, stepper motors provide exacting open-loop position control without the need for expensive feedback sensors. The invention of reliable transistors in the late 1950s made the digital control of these motors feasible, but it was the computing boom of the 1970s that drove mass production. Companies like IBM required highly precise, reliable, and low-cost motors to rapidly position the read and write heads in early floppy disk drives and hard disk drives. Engineers like Don McLeod pioneered new two-phase stepping motor designs specifically for the hard disk drive industry in the late 1970s, successfully competing against European manufacturers. Furthermore, stepper motors became the critical mechanical component in the manufacture of integrated circuits themselves. Wafer stepper machines, which emerged in the late 1970s and dominated the 1980s, used precise step-and-repeat camera systems to image millions of microscopic circuit elements onto silicon wafers, a process utterly dependent on the extreme positional accuracy of advanced stepping motors. Throughout the 1980s, drive circuits evolved from constant voltage drives to constant current drives, utilizing pulse width modulation, PWM, drastically increasing the practical operating speeds of stepper motors from a mere 60 revolutions per minute to over 1,000 revolutions per minute, firmly establishing them as the muscles of the digital revolution. While the alternating current induction motor was celebrated for its rugged simplicity and low cost, it possessed one glaring operational flaw. Its rotational speed was rigidly tied to the fixed frequency of the alternating current power grid, for example 60 Hz in North America, and the physical number of magnetic poles built into the stator. Achieving variable speed control with an induction motor in the early 20th century was exceedingly difficult, often requiring operators to resort to highly inefficient mechanical gearboxes, complex slip ring arrangements, or maintenance-heavy wound rotor motors that wasted massive amounts of energy via heat dissipation through external resistors. The ultimate solution emerged from the rapidly advancing field of power electronics. The invention of the silicon-controlled rectifier, commonly known as the thyristor, in the late 1950s, initiated a total revolution in the solid-state control of massive amounts of electric power. By the mid-1960s, innovative electrical engineers began utilizing banks of thyristors to develop the very first variable frequency drives, or VFDs, which could electronically alter the frequency of the power supplied to the motor. The story of commercial VFDs took a massive leap forward thanks to two Danfoss engineers, Arne Ryager and Arne Jensen, who heard a speaker at a London conference claim that regulating the speed of an alternating current motor could only be done mechanically. Determined to prove this wrong, the engineers successfully devised a method to create a realistic magnetic rotation field in a motor, regulate it at all speeds below the nominal speed, and safely manage the resulting heat. Their engineering breakthrough led Danfoss to achieve a massive historical milestone in 1968 by becoming the first company in the world to commence the mass production of alternating current drives, introducing the VLT5 drive, designed specifically for the variable speed control of standard three-phase induction motors. Concurrently, pioneering work in Finland at the Stromberg Company, led by engineer Martti Harmanen, resulted in the first commercial breakthrough of modern pulse-width modulation, or PWM, frequency drives, which were successfully utilized in the Helsinki metro system in 1972, further proving the viability of the technology for heavy traction and precise industrial control. By completely decoupling the motor's operational speed from the fixed frequency of the electrical grid, VFDs allowed industrial operators to precisely and dynamically control the speed and torque of alternating current motors with extreme accuracy. This capability allowed for exact process optimization across factories and yielded absolutely massive energy savings. Instead of running a pump or an industrial fan at full speed and throttling the output with a mechanical valve, which wastes immense energy, a VFD could dynamically reduce the motor speed to perfectly match the specific flow requirements of the system, drastically reducing electricity consumption, lowering mechanical wear, and providing soft starting capabilities that reduced mechanical stress on belts and gears. The engineering drive toward absolute motor efficiency was radically accelerated by sudden, severe macroeconomic trauma. In October 1973, the Organization of Arab Petroleum Exporting Countries, or OPEC, instituted an aggressive oil embargo in response to the Yom Kippur War, triggering a catastrophic energy crisis that caused global petroleum prices to quadruple virtually overnight. This sudden energy crisis generated massive lines at gas stations, severely disrupted the global economy, triggered staggering inflation, and forced Western governments and corporations to critically evaluate their rampant energy consumption for the first time in modern history. Subsequent intensive energy studies, most notably the famous Arthur D. Little report commissioned by the Federal Energy Administration and published in 1976, revealed a genuinely staggering statistic. Over 64% of all electric power generated in the entire United States was being consumed solely to drive electric motors. Furthermore, the industrial sector alone accounted for 27% of the nation's total electricity usage, with nearly half of all those motors operating liquid or gas handling equipment, like pumps and fans. The sudden realization that millions of continuous-duty industrial motors were operating constantly at suboptimal efficiencies prompted both a fierce market reaction and a sweeping legislative response. Motor manufacturers quickly recognized that energy efficiency was no longer a luxury, but a paramount economic necessity. Companies began prioritizing premium efficiency designs, deliberately utilizing more expensive copper, thinner, non-oriented electrical steel laminations, and highly optimized smaller air gaps to reduce magnetic and resistive losses. Simultaneously, the political landscape shifted decisively toward mandatory conservation. The United States Congress enacted the Energy Policy and Conservation Act in 1975, which laid the crucial foundational framework for federal energy targets, testing procedures, and labeling for consumer products. While the initial legislative efforts focused heavily on consumer household appliances, these early mandates firmly set the legal and political precedent that would eventually culminate in the strict, mandatory minimum efficiency performance standards for commercial and industrial electric motors, codified later in the Energy Policy Act of 1992. The desperate 1970s energy crisis also sparked early, highly ambitious corporate interest in electrified passenger transportation as a means to break dependency on foreign oil. In 1978 and 1979, the oil giant Exxon heavily funded research into an alternating current synthesizer, an early, highly advanced variable frequency drive. This synthesizer, developed by a former Massachusetts Institute of Technology electronics researcher named Baker, was designed to convert direct current power to alternating current and dynamically vary the frequency and voltage to precisely control the speed of an electric vehicle motor. Exxon successfully mated this synthesizer to a powerful alternating current electric motor to create a highly efficient hybrid powertrain prototype installed in a Chrysler Cordoba, which theoretically achieved 27 miles per gallon, and later a Toyota Cressida. Exxon was so confident in the technology, they purchased the Reliance Electric Corporation for over $1 billion to manufacture the components and market the product. However, the ambitious project was ultimately abandoned. The complex synthesizer technology proved far too expensive and unreliable for mass production at the time, and a sudden drop in oil prices in the early 1980s caused Exxon to rapidly divest from non-oil-related projects. Nevertheless, the effort vividly demonstrated how the shock of the 1970s energy crisis fundamentally altered the trajectory of electric motor application, setting the stage for the modern era of hybrid vehicles and high-efficiency drives. Power electronics and software, the invisible revolution. The miraculous physical architecture of modern electric motors undeniably provides the raw physical muscle for propulsion, but it is the explosive, exponential advancement in power electronics and algorithmic software control that provides the essential hyper-intelligent brain. A modern permanent magnet brushless motor cannot operate by simply plugging it into a direct current battery source. Without a perfectly timed, rapidly alternating electrical current to synthesize a rotating magnetic field, the internal magnets will violently lock into place and the motor will stall. This incredibly precise timing, demanding microsecond accuracy, is orchestrated entirely by the motor inverter and the electronic controller. The technical evolution of these components over the last 3 decades has been arguably more consequential and transformative than the physical redesign of the copper and iron motors themselves. For several decades, the undisputed standard component for handling the high-power electrical switching required within motor inverters was the silicon-insulated gate bipolar transistor, IGBT. These silicon-based semiconductor switches were solely responsible for taking steady direct current from a battery pack and rapidly pulsing it on and off thousands of times per second to artificially simulate the alternating current required by the motor's stator coils. However, as global industrial demand for higher operational efficiency, higher battery voltages, and increasingly compact automotive packaging escalated throughout the 2000s and 2010s, traditional silicon began to rapidly approach its inherent inescapable physical and thermodynamic limitations. Silicon transistors suffer significantly from operational inefficiencies known as switching losses and conduction losses. Every single time the silicon transistor forcefully transitions between its on and off states, a measurable amount of electrical energy is permanently lost as waste heat. When an inverter is forced to switch electrical currents thousands of times per second to drive a high-speed electric vehicle motor, these minute thermal losses compound exponentially. Consequently, engineers were forced to design massive, heavy, and complex liquid cooling systems simply to prevent the silicon-based inverter from melting under its own generated heat, severely limiting the power density of early electric vehicles. The technological leap that unequivocally defined the modern era of power electronics was the aggressive transition away from pure silicon and toward wide bandgap semiconductors, most notably silicon carbide and gallium nitride. In solid-state physics, a material's band gap refers specifically to the amount of energy required to free an electron from its home orbit so that it can move freely and conduct electricity. Silicon carbide possesses a band gap that is 3 times wider than traditional silicon, and it boasts a critical breakdown electric field that is an astonishing 10 times higher. This altered atomic structure provides profound, game-changing engineering advantages for motor control. Silicon carbide devices feature a thermal conductivity of 490 watts per meter Kelvin, vastly outperforming standard silicon, allowing them to easily withstand extreme electrical voltages. They routinely operate flawlessly at voltages exceeding 1200 volts and can comfortably tolerate internal junction temperatures exceeding 200 degrees Celsius, operating regimes that would instantly destroy standard silicon, which typically fails at around 150 degrees Celsius. Most importantly, silicon carbide permits vastly faster electrical switching speeds while incurring dramatically lower energy losses. Because these advanced chips lose significantly less energy as waste heat, they require much smaller, lighter, and less intrusive thermal management systems. The integration of silicon carbide has allowed automotive and industrial system designers to drastically shrink the volumetric footprint of the inverter, reduce the overall mass of the vehicle, and increase total powertrain efficiency to previously unimaginable levels. A recent exhaustive Swiss research initiative vividly demonstrated the sheer scale of this efficiency improvement, concluding that simply replacing traditional silicon-based variable speed drives with silicon carbide variants in global industrial pump systems alone could result in staggering annual energy savings of up to 25 terawatt-hours, highlighting the immense global impact achievable strictly through advanced semiconductor material science. However, the widespread implementation of silicon carbide not without immense manufacturing challenges. The production of silicon carbide wafers require pure silicon and carbon sources processed through highly complex methods like physical vapor transport, which operates at extremely high temperatures to grow single crystals. Growing defect-free silicon carbide boules is incredibly time-intensive, and global supply has struggled to keep pace with surging demand, leading to extended lead times. Furthermore, the industry is currently attempting a difficult transition from 150mm 6-inch wafers to 200mm 8-inch wafers to reduce manufacturing costs, an engineering hurdle fraught with yield rate issues due to the material's brittleness and susceptibility to microscopic crystal defects. Because automotive-grade inverters demand the highest possible reliability, yield losses heavily dictate the ultimate cost of modern high-performance drivetrains. Simultaneously, another wide bandgap material, gallium nitride, has rapidly emerged as the premier semiconductor choice for applications requiring exceptionally high switching frequencies and ultra-compact featherweight designs, such as high-speed drones, robotics, and consumer electronics. Gallium nitride boasts an electron mobility rating of up to 2,000 centimeters squared per volt second, which significantly exceeds that of silicon carbide, allowing it to achieve mind-boggling switching frequencies deep into the megahertz range, while maintaining pristine signal integrity and virtually zero switching loss. While silicon carbide currently dominates the high-power, high-voltage, extreme-temperature automotive and industrial sectors, typically above 650 volts, gallium nitride is entirely revolutionizing medium-power applications by enabling power densities 3 to 5 times higher than any legacy silicon equivalent. By heavily utilizing gallium nitride transistors in drone motor controllers, aerospace engineers can dramatically reduce the physical weight of the onboard electronics while exponentially increasing the precision and speed of the motor's response. This microscopic control directly translates to significantly longer autonomous flight times, vastly superior aerial stability, and instantaneous reaction to turbulent wind conditions. Hardware improvements in wide bandgap semiconductors, no matter how revolutionary, would be vastly underutilized without parallel, equally dramatic advancements in algorithmic software control. In the 1990s and early 2000s, early brushless direct current motors relied on relatively simple, rudimentary trapezoidal control schemes, or basic volts per hertz logic. These early systems utilized physical Hall effect magnetic sensors bolted inside the motor to roughly determine the general position of the spinning rotor, allowing the computer to guess exactly when to fire the next bulky electromagnetic pulse into the stator. While entirely functional for basic applications, this analog method was highly inefficient at low speeds, generated annoying acoustic humming noise, and suffered from severe control lag at high rotational speeds, heavily restricting the motor's true performance potential. The ultimate solution to this control bottleneck was a mathematical masterpiece known as field-oriented control, or FOC, a highly advanced algorithmic strategy that miraculously treats complex, chaotic three-phase alternating current motors as if they were simple, easily controllable direct current machines. The foundational concepts for field-oriented control were pioneered in the late 1960s and early 1970s by Felix Blaschke, a brilliant researcher at Siemens in Germany, who realized that to achieve the snappy torque response of a direct current motor in an alternating current machine, the controller needed absolute instantaneous knowledge of the rotor flux angle. Although the dense mathematical foundation for field-oriented control was conceptualized decades ago, it was entirely impractical and prohibitively expensive to implement until the recent advent of low-cost, high-performance microprocessors and digital signal processors capable of flawlessly executing thousands of complex trigonometric calculations per millisecond. To thoroughly understand the genius of field-oriented control, one must first understand the invisible forces battling inside a spinning motor. Magnetic fields interacting across the air gap generate two distinct competing types of force: quadrature force, or Q-axis, and direct force, or D-axis. Quadrature force runs entirely perpendicular to the magnetic pole axis of the rotor. This is the highly desirable force that creates actual useful rotational torque, physically twisting the motor shaft to drive the wheels. Conversely, direct force runs perfectly parallel to the rotor's pole axis. This is a completely useless, energy-wasting radial tension that attempts to pull the rotor violently outward toward the stator walls, but contributes absolutely nothing to forward rotation. The ultimate overriding goal of any high-performance motor controller is to relentlessly maximize the quadrature torque, while absolutely minimizing the wasteful direct torque to zero under standard operating conditions. Field-oriented control achieves this near-perfect optimization through highly intensive continuous mathematical operations universally known as the Clark and Park transformations. First, the processor measures the real-time electrical currents flowing into the motor. The Clark transform takes these three-phase, rapidly alternating, time-variant physical currents from the typical A, B, C stator phases and mathematically squashes them into a highly simplified two-dimensional stationary coordinate system known as the alpha-beta frame. The mathematics move to the Park transform, which takes those newly created stationary coordinates and mathematically rotates them to perfectly match the actual real-time spinning speed and angle of the rotor, creating the DQ frame. Through this incredibly heavy computational lifting, the microprocessor is no longer forced to interpret a chaotic, rapidly alternating three-phase electrical storm. Instead, it views the motor's operation as two simple, steady-state, time-invariant direct current values, representing the desired torque component and the undesired magnetic flux component. By completely decoupling these two forces in the digital realm, the software can employ simple, instantaneous, proportional integral feedback loops to independently adjust the voltage. It aggressively drives the user's desired throttle speed directly into the torque component, while actively forcing the direct flux component to remain at zero under standard operating conditions. Once the optimal response is calculated in the digital matrix, the algorithm runs the mathematical Clark and Park transforms completely in reverse, translating the perfect two-dimensional solution back into the exact complex electrical signals needed by the inverter to physically drive the motor phases. This final stage is typically executed using space vector pulse width modulation, or SVPWM. Unlike traditional sinusoidal pulse width modulation, which suffers from poor voltage utilization, SVPWM visualizes the possible switching states of the inverter as a mathematical hexagon containing 6 basic voltage vectors and 2 null vectors. By flawlessly alternating between adjacent active vectors and null vectors, SVPWM allows the inverter to utilize 100% of the available direct current bus voltage, a 13.3 to 15% improvement over standard modulation, drastically reducing total harmonic distortion and minimizing acoustic noise. Executed flawlessly at breathtaking frequencies of 10,000 to 20,000 times per second, field-oriented control completely eliminates unwanted torque ripple, allows the motor to generate its absolute maximum peak torque even at 0 revolutions per minute, and aggressively pushes total system electromechanical efficiencies well past the 95% threshold. The sheer computational intensity required to run field-oriented control, handle space vector modulation, manage thermal derating, and process fault diagnostics simultaneously requires incredibly robust microcontrollers. The industry has seen an aggressive evolution from basic 8-bit chips to massively powerful 32-bit automotive-grade processors. Prominent examples include the Texas Instruments C2000 real-time microcontrollers, which became an industry favorite for their highly optimized math engines and extensive motor control libraries. European semiconductor giant Infineon revolutionized automotive safety with their RX family of microcontrollers, introduced in 2012 and continuously evolving into hexacore architectures. RX chips process complex motor control algorithms while providing ironclad hardware-level functional safety to prevent catastrophic drivetrain lockups. Similarly, ST Microelectronics introduced the stellar 32-bit automotive MCU platform, designed specifically for the extreme demands of vehicle electrification, featuring phase change memory technology and the processing headroom required to run multiple real-time motor functions securely. The deployment of these powerful microcontrollers has fundamentally shifted the automotive landscape towards software-defined vehicles. In traditional legacy automotive engineering, a vehicle's mechanical capabilities were entirely fixed the moment it rolled off the assembly line. Today, the behavior of an electric motor is deeply malleable, continuously optimized via OTA software updates. Automakers like Tesla and Rivian frequently deploy firmware patches that physically alter the torque curves, regenerative braking aggression, and thermal management limits of their vehicles without touching a single physical bolt. For example, Tesla has historically pushed software updates that unlock up to 5% more driving range or enhance peak power output simply by refining the mathematical efficiency of their motor control algorithms and optimizing how the inverter switches current at highway speeds. Rivian has taken this software-centric approach further by completely redesigning the electrical backbone of their second-generation vehicles, moving away from a legacy architecture that utilized 17 distinct electronic control units scattered across the chassis. Rivian transitioned to a highly advanced zonal architecture. By consolidating computation into just a few centralized, incredibly powerful zonal controllers, designated East, West, and South, Rivian eliminated 1.6 miles of physical copper wiring from each vehicle. This software-driven consolidation not only removed 44 pounds of dead weight from the vehicle, directly improving the motor's effective range and efficiency, but drastically reduced communication latency between the battery management system and the motor inverters, allowing for much sharper, faster torque adjustments across complex terrain. Perhaps the most profound physics-bending capability unlocked by advanced software control is the technique universally known in the automotive industry as field weakening, perfectly balanced against maximum torque per ampere. When an electric vehicle launches from a standstill, the software strictly utilizes maximum torque per ampere logic. MTPA mathematically calculates the exact optimal angle to inject current to utilize both the raw magnetic pulling force and the geometric reluctance force of the rotor simultaneously, ensuring the vehicle accelerates violently while consuming the absolute minimum amount of battery current. However, as the motor spins faster and faster, the spinning permanent magnets physically sweep past the copper stator coils, creating a powerful reverse electrical pressure known as back electromotive force, back EMF. As vehicle speed increases, this back EMF grows linearly stronger. Eventually, the vehicle hits a critical velocity where this reverse electrical pressure perfectly matches the maximum forward voltage that the battery and inverter are physically capable of supplying. At this precise moment of equilibrium, known as the motor's base speed limit, no additional electrical current can be pushed into the motor, and the vehicle absolutely cannot accelerate any further. Through the sheer computational power of the field-oriented control algorithm, the microprocessor can intentionally decide to break its own cardinal rule of keeping the direct current component at zero. When the vehicle reaches its base speed limit, the software injects a mathematically calculated, heavily regulated negative electrical current specifically into the direct axis. This deliberate negative current forces the stator to generate a specific magnetic field that intentionally opposes, repels, and artificially weakens the field of the permanent magnets embedded on the rapidly spinning rotor. Because the effective overall magnetic field of the spinning rotor is artificially weakened by the software, the problematic back electromotive force generated by the motor drops significantly, relieving the reverse electrical pressure. With this pressure suddenly reduced, the silicon carbide inverter can once again successfully push forward current into the motor's coils, allowing the electric vehicle to continue accelerating to speeds well beyond its physical base speed limit. While this software-induced field weakening state does come at the unavoidable expense of reduced maximum available torque, as a portion of the electrical energy is now being consumed simply to fight the magnets rather than twist the shaft, it is an incredibly worthwhile trade-off for highway driving. It allows electric vehicles to seamlessly transition from low-speed acceleration directly into highly efficient, sustained, high-speed highway cruising using only a single, lightweight, fixed-gear transmission, fundamentally altering automotive packaging and manufacturing complexity forever. The electric vehicle and aerospace boom. The flawless fusion of high-frequency wide-band gap semiconductors and flawless algorithmic software control set the ultimate stage for a global mechanical renaissance. As the massive automotive and aerospace industries committed their vast resources toward total electrification, the demand for raw power density, microscopic efficiency gains, and extreme thermal management skyrocketed. This intense competitive pressure led to the rapid development of highly specialized, bespoke motor architectures that departed significantly from any traditional 20th century designs. The modern era of the mass-market electric vehicle was arguably ignited by Tesla, a company whose early groundbreaking vehicles, including the original Tesla Roadster, the flagship Model S, and the Model X SUV, relied entirely on alternating current induction motors. Induction motors, remaining remarkably true to the original designs patented in the late 19th century, do not contain any rare earth permanent magnets. Instead, they ingeniously use the stator's alternating magnetic field to remotely induce an electrical current across a cage of heavy copper or aluminum bars embedded within the rotor. This induced current, in turn, creates the secondary magnetic field required for rotational attraction. While induction motors are legendary for their rugged durability and are entirely free from volatile geopolitical supply chains, they harbor a fatal, unavoidable thermodynamic flaw regarding battery range. Inducing that massive electrical current across the rotor generates immense internal heat and routinely wastes up to 4% of the vehicle's precious battery energy merely to maintain the magnetic field, a loss that becomes particularly punishing during long-distance highway cruising. When Tesla engineers sat down to design the mass-market Model 3, they faced a brutal, unforgiving optimization problem. They needed to absolutely maximize the vehicle's driving range while simultaneously minimizing the size, weight, and astronomical cost of the lithium-ion battery pack. Their revolutionary solution was to completely abandon their namesake induction technology in favor of a groundbreaking, highly complex hybrid architecture known throughout the industry as the interior permanent magnet synchronous reluctance motor. This specific architecture represents an absolute masterclass in modern magnetic engineering and software control. Rather than crudely gluing delicate permanent magnets to the outer surface of the spinning rotor, where they could easily detach at high speeds, engineers instead utilized advanced computer modeling to cut complex, carefully calculated asymmetrical geometric grooves deep into the solid iron core of the rotor. Razor-thin strips of powerful permanent magnets are then deeply buried inside these protective cavities. In extremely high-performance variants, such as the Model S Plaid, Tesla pioneered a process to tightly wrap the entire spinning rotor in a carbon fiber sleeve to physically prevent the rotor from expanding and exploding under the immense centrifugal forces generated at speeds exceeding 20,000 revolutions per minute. This ingenious interior permanent magnet synchronous reluctance motor design leverages two distinct and incredibly powerful physical phenomena simultaneously to generate forward motion. First, it utilizes the raw, unadulterated magnetic pulling power of the buried permanent magnets interacting with the stator. Second, it aggressively harnesses the physics of reluctance torque. Magnetic fields, much like flowing water or electricity, constantly seek the path of least resistance. By cutting air-filled geometric grooves into the solid iron rotor, engineers artificially created areas of incredibly high magnetic resistance, known as reluctance, alongside areas of low resistance. The vehicle's high-speed motor controller aggressively and rapidly pulses the stator's electromagnets, forcing the heavy iron sections of the rotor to constantly, violently pull themselves into alignment with the easiest available magnetic path. By perfectly synchronizing the magnetic pulling force of the permanent magnets with the mechanical realignment force of magnetic reluctance, Tesla created a hybrid motor that routinely achieves astounding energy efficiencies. Because the fragile magnets are buried deep inside the solid iron, their magnetic flux is naturally partially shielded, making the software-controlled field weakening process required for high-speed highway cruising drastically more efficient and lowering the troublesome back EMF. Because this motor architecture relies heavily on the physical geometric shape of the iron to generate reluctance torque, rather than relying purely on raw magnetic strength, the total volume of expensive permanent magnets required per vehicle is significantly reduced. This hybrid architecture has proven so vastly superior in terms of raw electrical efficiency, thermal management, and high-speed dynamic behavior that it has since become the undisputed dominant technical standard across almost the entire high-performance electric vehicle industry. To this day, Tesla continues to refine this technology. The latest Performance 4DU drive unit, deployed in the newest Model 3 variants, features a bespoke magnetic design that delivers a 32% increase in peak power and 16% more torque, all while utilizing less electrical energy than the previous generation. As global automakers relentlessly push the boundaries of vehicle performance, the physical, metallurgical construction of the electric motor's copper vanes has undergone radical surgical refinement. A prime example of this extreme optimization is the industry-wide transition away from traditional stranded wire stator windings toward advanced hairpin and continuous wave W-pin winding topologies. Historically, electric motor stators were painstakingly wound by wrapping hundreds of thin, flexible, round copper wires around the iron teeth of the stator core. Because you cannot perfectly pack round circles into a square space, this archaic method leaves massive amounts of microscopic empty airspace between the individual wires, resulting in a poor slot fill factor of approximately 45%. Air does not conduct electricity, meaning over half the available space inside the motor was essentially wasted. Modern ultra-high performance motors now universally utilize hairpin winding technology. Instead of flexible wire, these stators use solid, rigid, rectangular bars of copper shaped like hairpins. These rectangular bars are machine-inserted into the stator slots by complex robotics, perfectly locking together flush against each other like puzzle pieces to radically increase the slot fill factor up to an astounding 80%. Cramming significantly more raw copper into the exact same physical volume drastically lowers the direct current or DC electrical resistance of the motor, improving overall energy efficiency by up to 20%, and aggressively pushing power densities from a standard 3.5 kilowatts per kilogram up to an elite 4.5 kilowatts per kilogram. However, solid copper bars are technically prone to massive alternating current losses at exceptionally high speeds due to a brutal physics phenomenon known as the skin effect and the proximity effect. As alternating current frequency increases during high-speed driving, the electrical current is pushed violently toward the outer skin of the copper bar, leaving the center of the conductor completely dead and unused, which paradoxically spikes the electrical resistance and generates immense heat. To combat this, automotive engineers utilize highly complex asymmetrical winding patterns, smaller bar designs, and continuous wave W-pin winding techniques. W-pin winding is a revolutionary manufacturing method that attempts to seamlessly form an entire winding layer from a single unbroken piece of flat wire, completely eliminating the need for hundreds of individual failure-prone laser welds at the crown of the stator. This not only dramatically improves the durability of the motor, but significantly reduces manufacturing costs and improves noise, vibration, and harshness behavior by balancing the electromagnetic fields. Cooling these hyper-dense, immensely powerful electrical power plants requires equal, if not greater, engineering innovation. Lucid Motors, an industry leader in powertrain miniaturization, achieved a staggering record-breaking power density of 14.7 horsepower per kilogram in their motorsport and production drive units by completely rethinking fluid thermal management. Rather than relying on traditional, bulky water jackets that merely wrap around the outside casing of the motor to passively absorb radiated heat, Lucid engineers developed a highly guarded, patented microjet cooling system. They meticulously machined microscopic fluid channels directly into the actual iron stator laminations themselves, allowing advanced automatic transmission fluid to flow intimately close to the actual copper windings where the heat is natively generated. As the fluid exits the internal core, it is violently sprayed directly onto the exposed copper end windings in a high-pressure jetting effect, instantly carrying massive thermal loads away from the core of the motor before the copper can melt. This extreme thermal extraction allows a single lucid drive unit, which is incredibly compact enough to physically fit inside a standard airplane carry-on suitcase, and cleverly integrates the planetary gear set differential directly inside the hollow spinning rotor shaft to continuously output over 670 horsepower without suffering any thermal derating. This immense power is facilitated by transitioning to extreme high-voltage electrical architectures. While legacy electric vehicles operated at 400 volts, pioneers like Porsche with the Taycan and Lucid with the Air operating at over 900 volts proved that doubling the voltage allows engineers to push the exact same amount of electrical power using half the current. Halving the current means the heavy, thick copper cabling connecting the battery to the motor can be drastically reduced in size and weight, saving precious mass and reducing heat resistance. Lucid's Wonderbox system further leverages this architecture by integrating bidirectional charging capabilities directly into the high-voltage silicon carbide circuitry, allowing the vehicle to take in energy at blinding speeds or output power back into the electrical grid. However, running 800 to 900 volts through a compact electric motor introduces terrifying new engineering hurdles, primarily a phenomenon known as partial discharge and corona discharge. As silicon carbide inverters rapidly slam massive 800 volts of electricity into the motor windings with incredibly steep rise times, the microscopic air pockets trapped inside the protective resin coating the copper wires begin to electrically stress. These air pockets begin to literally ionize and spark internally. This microscopic, invisible sparking, partial discharge, slowly and aggressively eats away at the chemical structure of the motor's insulation. If left unchecked, this high-voltage erosion will eventually bore a hole straight through the copper's protective coating, causing a catastrophic short circuit and instantly destroying the motor. Solving this requires entirely new classes of advanced, highly resilient dielectric resins and flawless void-free vacuum impregnation manufacturing techniques to ensure modern high-voltage motors can survive a 10-year lifespan without immolating from the inside out. Taking architectural innovation even further, the industry has seen visually radical departures from conventional motor design, most notably the rise of the axial motor. For over a century, over 99% of all electric motors utilized a standard radial flux topology, where a cylindrical rotor spins inside a larger hollow cylindrical stator, and the magnetic fields flow outward along the radius from the center. In a revolutionary axial motor, the entire architecture is flattened into a compact pancake shape. Two flat disc-shaped rotors sandwich a central stationary stator disc, and the powerful magnetic fields flow perfectly parallel to the axis of rotation. The physics inherent to this flattened design unlock absolutely massive performance gains for weight-sensitive applications. In a standard radial motor, the rotational torque generated scales proportionally to the square of the motor's diameter, but in an axial motor, because the active magnetic material is intentionally located at the farthest outer edge of the spinning disc, providing maximum physical mechanical leverage against the shaft, the resulting torque scales to the cube of the diameter. This profound geometric advantage allows engineering companies like YASA, which was recently acquired by automotive giant Mercedes, specifically to power their next-generation AMG electric supercars, to produce motors that deliver up to 4 times more torque and double the power density of traditional radial designs, while simultaneously being 50% lighter and up to 80% thinner. Furthermore, the axial topology inherently eliminates the need for a heavy, solid iron stator yoke, drastically cutting dead weight and allowing the motor to be incredibly power-dense. The vast, flat surface area of the winding discs allows for phenomenal direct contact cooling, meaning an axial motor can sustain its blistering peak power outputs almost indefinitely without overheating. Companies are utilizing both radial and axial extreme architectures to fundamentally rewrite vehicle dynamics through software torque vectoring. Companies like Rivian and Rimac have completely revolutionized driving behavior by employing quad-motor drive systems. By dedicating a completely independent electric motor and inverter to each individual wheel, they eliminate the need for heavy, complex mechanical locking differentials entirely. Instead, highly advanced software independently adjusts the exact torque output at each wheel hundreds of times per second. Rimac Automobile's record-breaking Nevera hypercar utilizes highly customized carbon-sleeved permanent magnet motors to deliver a mind-bending total of 1.4 megawatts of power, 1,914 horsepower, to the pavement. Its proprietary all-wheel torque vectoring algorithm reads the road ahead using cameras and sensors, calculating the exact amount of positive acceleration or negative braking torque to deploy to each specific wheel to artificially force the car to pivot around corners like a fighter jet. This pure software torque vectoring can instantly neutralize understeer or oversteer, providing physics-defying traction control that completely outperforms the physical limitations of any mechanical all-wheel drive system ever built, allowing the Nevera to shatter 23 performance records in a single day, including a 0 to 100 km/h acceleration time of a staggering 1.81 seconds. While the ground-based automotive sector spent billions optimizing for sustained highway efficiency, partial discharge resistance, and peak horsepower, the aerospace sector, specifically the explosive high-growth drone and unmanned aerial vehicle (UAV) industry, optimized entirely for pure thrust-to-weight ratios and instantaneous microsecond responsiveness. Modern, highly agile autonomous drones capable of navigating dense forests at high speeds or carrying heavy cinematography payloads rely exclusively on high-speed outrunner brushless motors. In an outrunner motor, the central copper coils are rigidly fixed to the drone's frame, and the entire outer bell casing, which is heavily lined with magnets, spins rapidly around the outside of the coils. This provides immense rotational inertia and massive mechanical torque leverage, allowing a very small motor to swing surprisingly large, aggressive propellers at high speeds. Drone motor performance is heavily defined by its absolute thrust-to-weight ratio and a critical metric known as the kV rating, which dictates exactly how many revolutions per minute the unloaded motor will spin per single volt of electricity applied. The sizing nomenclature for these motors is universally standardized. For example, a 2207 motor features a stator diameter of precisely 22 millimeters and a stator height of 7 millimeters, a size highly favored for aggressive 5-inch racing drones due to its perfect balance of torque and rapid RPM response. However, the defining, truly revolutionary technological leap in drone propulsion occurred in the microscopic software governing the electronic speed controllers, ESCs. An ESC is essentially a highly miniaturized, ultra-lightweight inverter responsible for translating the flight controller's directional commands into physical motor rotation in fractions of a millisecond. In the early 2010s, drone ESCs were highly rudimentary. They utilized basic 8-bit processors and relied on standard analog communication protocols like pulse width modulation, (PWM). These analog signals suffered from severe signal latency, electrical jitter, and slow update rates. If a drone encountered a sudden gust of wind, the flight controller's desperate analog command to the ESC to increase motor speed took entirely too long to process. Early open-source firmwares like Simon K and the original BL Heli began to push the limits of these 8-bit chips. Simon K provided drastically faster throttle response times than anything previously seen, but it was the introduction of active braking, often referred to as damped light, in BL Heli that fundamentally changed aerial agility. Active braking allowed the ESC to actively reverse the motor's magnetic field to instantly stop a spinning propeller the moment the pilot lowered the throttle, allowing a drone to drop altitude instantly and execute physics-defying acrobatic maneuvers rather than floating lazily in the air due to propeller momentum. The true paradigm shift occurred with the transition to 32-bit ARM processors running advanced firmware like BL Heli 32, the ultra-smooth proprietary KISS firmware, and the open-source AM32. This raw processing power allowed for the invention of the D-Shot protocol. Instead of sending varying analog electrical pulses that could easily be corrupted by electromagnetic noise from the battery wires, or suffer from oscillator drift, the flight controller now sends absolute high-speed, incorruptible digital data packets directly to the ESC. The most advanced iterations of this technology, such as bidirectional D-Shot, enable hyper-fast two-way communication. The ESC not only receives speed commands, but simultaneously streams the exact real-time motor RPM telemetry data back to the central flight controller at thousands of times per second. This allows the drone's central brain to apply incredibly complex RPM filtering, mathematically calculating the exact resonant vibration frequencies being caused by the spinning motors and erasing that physical noise from the sensitive gyroscope data in real time, long before it can destabilize the control loops. Scaling the principles of high-performance drone flight up to human-carrying aircraft has birthed the burgeoning electric vertical takeoff and landing (eVTOL) industry. Companies like Joby Aviation, Archer Aviation, and Mighty Fly are fundamentally rethinking commercial aerospace utilizing distributed electric propulsion architectures. Unlike a traditional helicopter relying on a single massive combustion engine and a complex, failure-prone mechanical gearbox, eVTOLs utilize multiple highly efficient electric motors spread across the aircraft's wings and tail. This distributed architecture provides absolute, unprecedented safety through multi-level redundancy. The Joby Aviation S4, for instance, utilizes 6 articulating proprotors, but crucially, each proprotor is driven by 2 completely independent dual-wound electric motors. If one entire battery network or a motor controller catastrophically fails mid-flight, the secondary independent motor windings immediately take the full load, allowing the aircraft to continue hovering and land safely without any critical function lost. Similarly, the Archer Midnight utilizes 12 separate electric motors. Its proprietary control software is designed to instantly detect a motor failure and autonomously adjust the torque and pitch of the remaining 11 motors to maintain perfect stability, a feat of digital balancing entirely impossible with combustion engines. Because pure battery weight remains a massive limitation for long-range flight, heavy hybrid solutions are actively emerging. The Mighty Fly Centro, an autonomous cargo drone designed for 600-mile logistics routes, utilizes 8 electric vertical lift fans for takeoff, but incorporates an onboard internal combustion generator to continuously recharge the batteries mid-flight. This prevents the aircraft from being grounded for hours to recharge, allowing for continuous multi-stop commercial delivery runs. Meanwhile, for larger traditional fixed-wing aircraft, companies like Magniac are producing aviation-grade electric propulsion units like the Magni 650. Operating at an incredibly dense 700 kilowatts of peak power, while weighing only 206 kilograms, these massive oil-cooled high-voltage motors are actively undergoing rigorous FAA certification testing to retrofit existing commuter airplanes, proving that megawatt-class electric propulsion is no longer theoretical. Current constraints and future horizons, 2020s and beyond. Despite the monumental, breathtaking engineering achievements of the last 30 years across the automotive and aerospace sectors, the global transition to fully electrified transport is currently facing a severe, potentially existential bottleneck. The very materials that make compact, high-efficiency permanent magnet motors physically possible, rare earth elements like neodymium, dysprosium, praseodymium, and terbium, have unfortunately become a profound geopolitical, economic, and environmental liability of global proportions. The scientific nomenclature rare earth is technically a misnomer. These elements are relatively abundant within the Earth's crust. The global crisis stems entirely from the fact that they are exceedingly difficult, exorbitantly expensive, and horrifically environmentally devastating to extract, separate, and refine into usable magnetic metals. The modern global supply chain is characterized by extreme, unprecedented geographic and political concentration. The People's Republic of China currently controls roughly 60% of all global mining output, processes an overwhelming 90 to 95% of the raw extracted materials, especially heavy rare earths like dysprosium, and ultimately manufactures over 90% of the world's high-performance permanent magnets. The absolute epicenter of this global monopoly is the Bayan Obo mining district in Inner Mongolia, officially the largest and most heavily exploited rare earth deposit on the planet. The environmental toll of securing these magnetic materials for the Green Revolution is staggeringly bleak. The extraction and separation of rare earth elements require incredibly complex hydrometallurgical techniques that consume and subsequently dump massive, unmanageable quantities of toxic chemicals, including heavily concentrated sulfates, ammonia, and harsh hydrochloric acids. Processing just one single ton of rare earth metals generates an appalling 2,000 tons of highly toxic waste. Furthermore, rare earth ores are almost ubiquitously laced with dangerous radioactive elements like thorium and uranium, which are unearthed and concentrated during the mining process. In Bayan Obo, massive, unlined artificial tailings ponds spanning over 10 square kilometers are brimming with thick, black toxic sludge and highly radioactive waste. This toxic runoff has severely and permanently contaminated local groundwater tables, slowly trickling toward the Yellow River, devastating local agriculture, causing horrific livestock deformities and sparking severe human health crises in surrounding cancer villages. Compounding this unfolding environmental disaster is the harsh geopolitical reality. In 2010 and 2011, sudden export quotas imposed by China caused the prices of rare earth metals to violently spike by up to 900% in less than a year, sending shockwaves of panic through the global automotive and defense industries. Today, as electric vehicle production soars, Western nations have suddenly realized their most critical technological infrastructure is entirely dependent on a single, increasingly adversarial supplier who has recently implemented strict new export controls on critical processing technologies. This geopolitical weaponization has forced top automotive executives and aerospace engineers to urgently seek alternatives. In response, massive investments are being poured into advanced recycling technologies. Companies like Hypromag are commercializing patented hydrogen processing of magnet scrap technology. Traditionally, extracting glued, nickel-coated magnets from shredded electronic waste or old EV motors was nearly impossible. The HPMS process exposes the scrap to hydrogen gas, which specifically attacks the neodymium iron-boron alloy, causing it to violently expand and break apart into a demagnetized, friable powder that can be easily separated from the surrounding plastic and copper, allowing the rare earths to be infinitely recycled back into brand new high-performance motor magnets without tearing open the earth. The intense existential pressure to eliminate dependency on volatile, unethical supply chains has also sparked a massive, well-funded renaissance in completely magnet-free motor design. Engineers are eagerly revisiting older, previously discarded motor topologies that were deemed too inefficient in the 1990s and retrofitting them with today's advanced, ultra-fast computational software to make them highly viable. One of the most promising avenues is the heavy-duty switched reluctance motor. Unlike a modern permanent magnet motor, an SRM contains absolutely no magnets, and unlike an alternating current induction motor, it contains no heavy copper windings on its rotor. The rotor is remarkably simple, cheap, and indestructible. It is simply a jagged piece of solid laminated steel engineered with prominent gear-like teeth. The motor operates purely on the raw physical principle of magnetic attraction, as the heavy stator electromagnets surrounding the rotor are energized in a rapid, specific sequence. The steel rotor teeth are violently pulled into alignment to minimize the magnetic reluctance within the air gap. Historically, SRMs were notorious for horrendous, deafening acoustic noise and brutal torque ripple. The physical, chassis-shaking shuddering caused by the aggressive, sequential snapping of the immense magnetic fields. However, by utilizing the exact same ultra-fast microprocessors and wide bandgap inverters that enable field-oriented control, companies like Turntide Technologies have successfully developed highly advanced, smart, software-defined SRMs. By flawlessly profiling the exact physical geometry of the motor in the digital realm, the controller can manipulate the timing, shape, and intensity of the electrical current pulses precisely as the rotor teeth align. This highly complex current profiling actively cancels out the resonant vibrations, aggressively smoothing the torque delivery and silencing the motor. These modern SRMs can now routinely achieve peak efficiencies of 95%, matching permanent magnet motors, making them a premier, geopolitically secure choice for massive commercial HVAC systems and heavy industrial machinery. Simultaneously, major global automakers are aggressively pioneering externally excited synchronous motors to completely circumvent the rare earth monopoly. BMW, a pioneer in EV technology, has boldly eliminated rare earth magnets entirely in their 5th and 6th generation electric drivetrains. Instead of using expensive permanent magnets to create the necessary magnetic field on the rotor, engineers physically wrap copper wire coils directly onto the spinning rotor itself. To safely transfer high-voltage electricity into these rapidly spinning coils without permanent hardwired attachment, BMW utilizes an advanced, perfectly sealed module containing highly durable carbon brushes and a contact commutator. By utilizing a secondary electrical current to actively excite the rotor coils, the vehicle's computer gains ultimate, infinite control over the rotor's exact magnetic field strength at any given millisecond. This allows for highly efficient, drag-free coasting without the permanent magnetic resistance found in standard EVs and permits perfect instantaneous optimization of field weakening at highway speeds. German automotive suppliers Mahle and ZF are taking the ESSM concept even further by eliminating the physical brushes entirely to reduce maintenance. The Mahle MCT, magnet-free contactless transmitter, and the ZF I2SM utilize an ingenious inductive power transmission unit. They essentially build a miniature wireless charging coil directly inside the spinning rotor shaft, allowing the stator to wirelessly beam the required electrical excitation energy straight into the spinning rotor coils using high-frequency magnetic induction. This contactless design eliminates all mechanical wear, requires absolutely no rare earth metals, and operates at a benchmark 95% efficiency, proving that the future of high-performance automotive propulsion does not legally require Chinese neodymium. The rapid acceleration of artificial intelligence and generative design is currently reshaping how engineers conceptualize the physical layout of these next-generation motors. By utilizing advanced machine learning algorithms and physics-based diffusion models, engineering firms can input their required torque, efficiency, and thermal constraints, and the AI will autonomously generate hundreds of bizarre, highly optimized asymmetrical rotor and stator geometries that human engineers would never naturally conceptualize. This human-AI co-creation drastically accelerates the prototyping phase and squeezes every last drop of electromagnetic efficiency out of the iron and copper. Simultaneously, material science is aggressively pushing the absolute boundaries of atomic structure. A highly anticipated, industry-altering breakthrough is the ongoing commercial development of iron nitride, Fe16N2 permanent magnets. Spearheaded heavily by innovative American companies like Niron Magnetics, iron nitride represents the very first true commercially viable alternative to Chinese-dominated rare earths for applications where high magnetic strength is absolutely required. By utilizing incredibly abundant, cheaply and domestically sourced iron and nitrogen subjected to complex crystal structure stabilization processes, these revolutionary magnets offer a highly sustainable, conflict-free solution. Because iron nitride inherently possesses a physical characteristic of low coercivity, resistance to demagnetization, modern engineers pair them with highly advanced variable flux motor designs, allowing the overall magnetic field of the motor to be easily manipulated by the software inverter on the fly, drastically improving electric vehicle efficiency by an estimated 20 to 30% at highway rotational speeds. Looking much further over the technological horizon, the absolute undisputed pinnacle of electric propulsion physics lies in the realm of superconductivity. For the commercial aviation industry to truly decarbonize and move beyond heavy, short-range battery limitations, the industry desperately requires multi-megawatt class electric motors that are exceptionally lightweight. Existing traditional copper motor technologies simply cannot meet the brutal thrust-to-weight ratios required for large, single-aisle passenger aircraft. The immense amount of copper required to generate 5 megawatts of power would be too heavy for the plane to physically take off. To shatter this physical barrier, organizations like NASA, operating in tight conjunction with private aerospace engineering firms like Kinetics, are currently developing fully superconducting motors, such as the ambitious high-efficiency megawatt motor project. These futuristic motors utilize highly advanced superconducting wires, such as multi-filament magnesium diboride or complex bismuth-based alloys, which exhibit the miraculous quantum property of absolute zero electrical resistance when cooled below a specific, incredibly cold critical cryogenic temperature. By entirely eliminating electrical resistance, these superconducting wires can carry massively higher electrical current loads without generating any thermal losses or waste heat, allowing for the creation of immense magnetic fields and absolutely unprecedented mechanical power output from a microscopic package. The primary historical barrier to deploying superconducting motors outside of a laboratory has always been the immense prohibitive weight and complexity of the massive external cryogenic cooling compressors required to keep the wires freezing in mid-air. However, next-generation aerospace designs, such as those by Kinetics, feature brilliant cryogenic-free, fully integrated sub-20 Kelvin Stirling cycle coolers built directly into the rotor shaft. Alternatively, future aircraft designs ingeniously plan to utilize the aircraft's own onboard liquid hydrogen fuel reserves, which must inherently be stored at a frigid -253 degrees Celsius, as a massive built-in thermal heat sink to easily maintain the superconducting state of the powertrain as the fuel naturally flows to the fuel cells or combustion chambers. These ultra-high power density superconducting machines aim to deliver staggering operational efficiencies exceeding 99%, drastically reducing the heat rejection requirements that currently plague aviation design. Such a monumental technological leap is widely considered the only viable, realistic engineering path capable of powering the future of fully electrified commercial jumbo jets, completing the electric motor's two-century journey from a simple copper wire spinning in a cup of mercury into the quantum-cooled, software-defined engine of the future. The electric motor is arguably the most transformative mechanical device ever conceptualized by human engineering. Standing as the absolute foundation of modern infrastructure, industrial automation, and contemporary mobility, it has evolved from a 19th-century scientific curiosity into the hyper-intelligent, software-defined heart of the 21st century. From its initial conceptualization in the early 1800s, following Michael Faraday's groundbreaking discovery of electromagnetic rotation, the electric motor fundamentally altered human capabilities and reshaped the global economy. Initially designed to replace steam engines and manual labor, these early devices relied on simple interactions between magnetic fields and electrical currents passing through wire windings to generate the Laplace force, culminating in rotational torque. However, the landscape of electromagnetic propulsion today is entirely unrecognizable from its 20th century origins. Electric motors have transcended their legacy roles as simple, rudimentary industrial workhorses to become the highly intelligent, algorithmically driven propulsion centers of high-performance electric vehicles, autonomous aerial drones, renewable energy systems, and advanced robotics.